Pretty good group here. Shall we get started?
Yeah, let's do it.
So we are on week 2 of our mini series on building ZIO from scratch. So last week, right? It's crazy how time flies. Kit did an amazing job of kind of taking us from nothing to like a pretty like real world thing where we were doing like concurrency and we were implementing like zip par. So I think like really impressive like first week of ZIO from scratch. But I think there's definitely more work to be done. So let's dive in. Let me share my screen.
Let's do it.
Okay, and I'm gonna make things super big right now because I've gotten feedback that sometimes people can have trouble seeing. So I think that's about as big as I can make it and still be functional. Is this good for people?
That's intimidatingly large text there.
All right, awesome. And let me just see. So for last week, so yes, we always record the video. Basically, like any ZiVerge thing, if it's like a training, if it's a symposium, like it's always going to be recorded absent catastrophic technical difficulties. So it's coming. I think that particular one is not out yet. We will try to get that out, and maybe for this particular series, we'll try to kind of compress that timeline a little bit so that you can kind of catch up on the previous one before the next one. But there's just a little bit of lead time of like, we got to edit a little bit and kind of get it into kind of the queue of things to get out. So it's coming, but I don't think it's here today.
Could you do maybe a brief recap?
Overview? Yeah, I think that sounds fantastic.
I'll also post a link to the repo. So if you want to just explore the code in the background, there's not much really. It's like 80, 90 lines or something.
Yeah. So our goal with this whole session is to build up to something that is at least approximating ZIO and kind of do it together so we see that there's no magic there and we can all really understand it better ourselves. And so we started out with this simple trait ZIO that right now just has one type parameter. So versus the REA, it's just got the A so far. It's growing up to be the full ZIO.
So one other slight suggestion: could we close the terminal just during this overview part?
Yes, I think that's actually a wonderful idea. Yeah, and maybe we can see how I do without it. Normally, I kind of follow the SPT compilation errors, but yeah, I think that's a great idea, especially with my super large font. So right now we've just got this ZIO that's a description of a workflow that can eventually succeed with a value of type A. And we've implemented some basic operators in it. So in terms of constructors, we have this one called succeed that lets us lift any value into a ZIO computation and is going to suspend any side effects that are involved in that value. So we could use that to either do like ZIO succeed 1 or ZIO succeed print line hello world. So that's kind of the basic constructor, just bring synchronous code into ZIO. We also have this async constructor that lets us import any kind of callback-based API for asynchronous code into ZIO. And then we've got a couple of basic operations. We've got map that just lets us transform the value of this computation. We've got flat map that lets us do one computation and then do another computation after that. And then we've used those to just implement a few helpers like this as that just lets us kind of substitute a new value in for the existing value. Zip that just kind of takes two values, puts them together. And then probably the fanciest ones were we had this fork operator that lets us actually fork a fiber, which is you could think of as like a running computation. So almost like if we think about like ZIO versus future, we say like ZIO is just a description, nothing's happening until we run it. Future, when we touch it, usually it's already running. And so fiber you almost could think of as ZIO's equivalent of a future of when you see a fiber really is already in motion. It's doing something as soon as you're seeing it. Which is why this is actually suspended itself in a ZIO effect. If this is a description of creating a fiber that when you create it is going to run and do something. And we use that to implement this zip par operator. And the way that worked was we just forked one thing, we forked the other thing, and then we waited for both of those. And right now, the way we've implemented all of these is what I would almost call like probably a hybrid in a way between a declarative and an executable encoding. So an executable encoding, a fully executable encoding, every time we did one of these operations, we would just do the thing. So like when we had a flat map, we would actually like get the result and we would use it and we would do something else with it. And we're not being fully executable because we're not doing that. We're just returning this data structure, this thing that just is a ZIO.flatmap. But what maybe makes it a little bit less than fully declarative is each of these operators, like each of this ZIO flat map, it says, well, here's how to run me. And so we're not in a way fully separating the description of our program with how our program can be run, because each part of our description kind of comes with it its own instructions of here's how to run me. Which I mean, I think is a really nice kind of style, especially kind of for first getting started with something, and sometimes can be like the right style overall. But one of the things I think we're going to do as we evolve this is we're going to move to being even more declarative and really completely separate this description of each step in the ZIO workflow from how we're going to execute that step. And we're going to see as we start to dive in today some of the reasons that we might want to do that. So each of these have these little instructions of how to run them, and some of them are really simple of like, so each of these run methods right now takes a callback and just says what to do with it. So like if I'm succeeding with a value, then I just call the callback. If I've got an effect I've suspended, I just run that thunk here and I call the callback. Some of them end up being a little bit more sophisticated, but honestly, all these are like pretty straightforward as you work through them of like, if I have this flat map where I have like one ZIO and then I have another ZIO, then I just run the first one and the callback I give to it just says, perform this function to get a new ZIO and run that and give that to the original callback. So just with this, we were able to implement some pretty like real world type stuff of like by the end here, we had this like zip-par example, or let's see, where we have, oh yeah, here we go. So here we basically had this asynchronous computation that was going to like print line it was beginning, was going to sleep for 1 second, and then was going to complete with a random number. And we were able to use this zip-par to run 2 of these at the same time, and then get back both of the results. So let me see if I can, oh, maybe I can just, will that work? Maybe if I figure out how to bring back my terminal here. All right, I'm going to do it the old-fashioned way. Let me do run here. And so we see immediately we get the message that both these are starting, then we wait for these results. And I think right now we just, at the end of every program, we just wait a few seconds. We could probably cut that down. So pretty cool, like initial progress, but definitely more to do. So we've got a little bit of a kind of, I think, things we sketched out here of things we wanted to do. Maybe we can flesh that out a little bit and make ourselves a to-do list, and then we can start diving in here. So I think first thing that might be on kind of the to-do list here would be stack safety.
New execution context. GitHub Copilot wanted to do that. I don't know if we want to do that, but that was GitHub's idea.
That's funny.
Oh, by the way, could you close the side panel?
Oh yeah, yeah.
I think it's Command 1 will close it. I could be crazy.
It doesn't seem to be working for me, but I'll do that.
Oh, that works too.
Okay, there we go. Okay. So I think first thing we might want to like take here that's pretty basic is stack safety. So I don't think we illustrated this last time, and maybe we can do that in a second here. But this current implementation isn't stack safe if we have really long running computations. So if we go down to this flat map thing and the way it's implemented, every time we do a flat map, we're basically adding one more thing to the stack frame, because we're saying run this, and then we're adding this additional continuation. And so what that means is if I do something like I just try to like print something a million times with this current version of ZIO, we're going to blow up, which is definitely not what we want, because we want to be able to use this for like big complex applications. They're going to do lots of things. So that's definitely not going to work for us. So I think stack safety is one thing here that we'd like to be able to work on. I think actually to that point about the execution context, right now we don't have the ability to control where these effects are executed. So we kind of just did the shortcut here of every time we started a fiber, we just submit it to this global execution context, which is like probably a great place to start, but eventually we're going to want to be able to control where it runs. And one of the things we're going to want to avoid there is the situation we get into with Scala Future, where we end up basically, we need like anything you do with Future, you need to provide an execution context. And then, okay, let's make it a little bit easier. They make it implicit, but then like that has its own issues, because even though it's implicit, like every time you define your own operator that works with Future, you then need to have your own implicit execution context, which makes all your method signatures annoying through your whole code base. And also can result in problems when you actually go to run your code, where it may not be clear which execution context you're actually running on, depending on which implicit you have in scope. And you can have situations where like you copy something from one file to another, and the meaning of your program now completely changes because something's running on a different execution context, and maybe it's the wrong execution context. It's causing lots of problems for you. So these are two pretty basic things that I think we'll be able to tackle today. A couple of other things. There's a little bit of an issue around concurrency safety right now with forking and joining that we saw at the end of the last session. So I think with our symposium time, we may be able to hit on that too. Then a little bit of fancier things that we can look at.
Heterogeneous.
Yeah, these autocompletes are really funny. Error handling is definitely one of, we've got kind of the A, we don't have the E or the R of the ZIO REA. So eventually we want to get both those in. Probably the natural evolution is kind of the error type first and then the environment type. And another big one is interruption. So interruption is kind of one of the other like key features of ZIO, of like why you use a library like ZIO instead of something like Future, is there's really no principled way to interrupt a Future versus you can interrupt the ZIO computation. And for resource safety and efficiency within large applications, that's really important. So we don't have unnecessary work that's just kind of spinning off in the background forever. So those are some features that we'd like to add. And I think probably all of these are going to take more than we have today. But this will give us a little bit of a roadmap. And then over the next couple of sessions in the series, we can kind of come back to this and we'll kind of tackle one of these features at a time and try to build those out. And I think as we go through also, like either during these sessions or between them, if you say like, hey, I'm like really interested in X, like we can kind of try to prioritize that feature versus one of these other features. But I think right now, the initial focus is going to be on the stack safety issue. And just to illustrate this, I guess this is the, I'm not quite sure how to both never have this around as well as navigate between these two things. Well,
I think if you hit Command P, can you Command P?
Yeah, I think maybe I can have these on top here.
Like reasons P.
Yeah, let's see. Okay, there. All right,
Okay, cool.
Perfect. Okay, so let's create a new. Let's call this object stack safety. This will extend the little ZIO app thing. And maybe to motivate this, I'm actually going to give myself maybe one other, or maybe a couple of other operators.
Repeat N or something?
Yeah, exactly. Because I want to be able to do something a bunch of times so that I can illustrate blowing us up. So yeah, why don't we call this like repeat n, and it'll take an int, and it'll take a ZIO. That right now is a ZIO.
I think you're on the trait, so you could just.
Oh, excuse me.
Or you could just
Yeah,
delete.
yeah. Actually, well, I don't need the ZIO, but yeah, I think I'll do this on the trait.
Yes, no, that's great.
At least for the heck of it. And this will actually, right now, let's have this, what the heck, let's have this give us, right now, let's just have this give us unit right now. This will just kind of do these things and throw away the result. We could kind of imagine a version that like collects all the results into a list, but right now we'll just do this. And so here we could say if n is less than or equals 0, then we're done. We don't have to do anything. And otherwise, we will run this. And then I'm going to give myself another little helper here that ends up being useful. So I'm going to define this thing called, well, maybe I'll actually let's do zip with first. This is the problem. There are like so many like operators you're used to with ZIO. Sorry, that, which will be a ZIO. Thank you. And then this is actually a C as well. And so maybe I'll copy the implementation from zip here. And I'll just have this do F. And then, yeah, I can just re-implement zip in terms of that. And then I can have another one that I'll call zip right. And this will just give me the B. And so then this can just be zip with that. Exactly. And the star arrow one is kind of the one that I really wanted, but we had to build up slightly to it. So now that I got the star arrow, I can just say, okay, so if I still need to repeat more, then I should run myself. And then I should just call repeat again with one less repetition. So let's now, let's see oops. Do I have a compilation error here? I think I may be missing a brace here. Go. Okay. So now let's try, say my program is going to be ZIO.succeed, print line. I like howdy. I think it's introduced that. It's very nice. Repeat, and we'll start by just repeating 10. And so here we'll say run is my program. And now let's see if I can actually run that. Okay, I've got some compilation errors here. So,
so we did want to keep I guess the execution context.
Oh. Wait, do I want to keep this?
Value run is not a member of ZIO. Yes, it is.
I feel like we just like, did we just accidentally like delete something?
Yeah. Yeah, it's definitely missing. In fact, yeah. So it looks like we've somehow deleted run. That's no problem because I have the signature right here. I'll copy it.
I think, yeah, sometimes this is like pair program is usually pretty good, but occasionally you can like overwrite each other, which maybe we did.
A to units. Yes. Is that right or A? What do we get back? Oh no, just unit. Yes.
Unit. Yep.
There we go.
We're all callback based. Yep.
Yeah.
Okay. All right. So let's see if I can run this again. Okay, great. And let's see, what's my stack safety is 1 now. Okay. So I printed howdy 10 times. Awesome. Let's see what happens if I try to print howdy 100,000 times. Death.
Oh no.
So we scroll up and we see we started trying to print this and we got a stack overflow error. So this is definitely not going to make our users happy. So let's think about how we can address that. So we go back here, the problem is basically in this implementation of flat map here, where every time we run one of these, we're just adding a continuation of the stack frame. And so if we add 100,000 of them, that's more stack space than we have, and we blow up. So what we'd really like to be able to do is basically when we have these continuations, instead of just adding them to the stack frame, we'd like to be able to like add them to some actual like data structure where we could more explicitly like keep track of them and put them on and take them off ourselves so we don't just blow up here. But that's where we run into a little bit of an issue with this kind of hybrid encoding, because what this run method here, essentially this run method, like all it knows is its local state, right? It knows like, hey, I'm a flat map. I have this previous thing that I need to run, and then I have this other thing. But it doesn't have any other information about the broader context that's being run in. It doesn't know like how many stack frames have been used before, what other continuations need to exist, what executor am I supposed to be running on? It kind of, its information is still pretty local at this point. And when we think about that trade-off between declarative and executable encoding, one of the advantages that we go to a more and more declarative encoding is it means that we can separate out the running of the application into one place. And that means we have more information about what's going on and where we are in the computation as we're running it. And so basically the approach I'm going to take here is I'm going to try to pull all of these run methods out into one like super run method that's going to handle all of the running. And that's going to allow me to keep track of more state as I'm running in a way that is not going to make the API less attractive to my users. Of like, if I really wanted to keep this, I could have this world where like every time you call run, you keep track of some stack of continuations. And I kind of use that to have the stack safety. But like, that's really not going to be nice for our users of like, every time we call run, there's this like stack thing and what are they supposed to do with it? And they could mess it up and it's probably not going to have type safety. That's going to be kind of really ugly. So we're instead going to want to pull all that out into one place where we can kind of manage all of that internally and our users don't have to. Any questions on that, or does that make sense for everyone before we go on?
Not yet, but I'll let you know if any come in. Yeah, that can be a little tricky, but yeah, sort of the main purpose of this is for us to, just to reiterate, is to, or the motivation here is to, instead of relying on the default Scala language JVM stack, we're going to have our own stack in heap space that can grow as large as we want to fill up all the memory in the world, instead of the sort of the relatively small limits that are placed upon the stack. I think we could probably run up to like 8,000 howdies, but obviously it gets complicated, especially if you want to have something that's running forever in the background. It's just not tenable. So
yeah,
let's do it.
We don't want our howdies limited. All right. So what we're basically going to do here is, instead of this run method being abstract and implemented in each of these cases, we're going to implement the run method here. And so the easy way I'm going to do that and kind of get the compiler to help me here is I'm going to make this final. And so as soon as I do that, and now I'm going to do this, maybe I can make it smaller, but basically I'm going to kind of do the like following the compilation error thing. So I think I've got this other.
I think you just fixed that actually.
Oh yeah, okay, perfect. Okay, yeah, now I've got these. So basically now these are saying like, hey, you're overriding this thing that was final. So, okay, I'm gonna start by just commenting these out. I may want to reuse some of the logic here, but right now I'm just gonna take these out. And so now if maybe I make this solid, yeah, there we go. Okay, so now this is compiling. Obviously I can't run anything because as soon as I run, I'm just gonna blow up. So now let's start to work through what the implementation of this looks like. So the most basic thing I can do here is I say like, okay, it's got to be one of these different cases of ZIO. So I could just say self match And I think weirdly, this is actually not all the cases of ZIO, I think, because we're missing at least flat map. I don't know what the deal is with that, but
Yeah, it looks like the only one missing.
I don't know. Yeah, I'm not sure why I didn't get that one, which is kind of interesting. So we've got these 5 cases we need to handle. And let's just work through that a little bit iteratively. So the simplest one in a way is like if we see a succeed. So if we see a succeed, then all we need to do is, okay, we're given an A and we've got a callback that's gonna take an A. So all we need to do is call a callback. And similarly, if we've got like this effect, remember that's like the thunk, the open parentheses, close parentheses to an A, then we just have to evaluate the thunk and we can give it to the callback. So now the next one here that like is going to be like a little trickier and is going to kind of push us on our thinking here is this flat map one. And this flat map one is challenging because we've got this computation that we want to run next. And then we've also got this other continuation. And so this is going to really, like the previous ones, we kind of were able to implement the same way. This is really going to push us to use some of this functionality we've got here, or at least the ability to have functionality that we have in this run method. So what I'm essentially going to want to do is I'm going to want to run this, and I'm going to want to put this one onto my stack and my like heap stack that I'm going to create. So to do that, I'm first going to create a couple of just like helpers for myself here. So I'm going to define this new type that I'm going to call erased. And erased is just going to be a ZIO of any. So it's going to be a ZIO where I've forgotten all the type information about it. And that's going to be important because when we do this technique of creating like this run loop, we're essentially kind of taking all the ugliness of the world that like needed to exist somewhere, and we're kind of sucking it into the run loop and like just containing it there so that everything else can be really nice. And so one of the things that we're going to see here is as we go through this stack of continuations, the type of the ZIO may change, right? Because we might start with like ZIO succeed 1, and then we might do like map to string, and then we might do map string.length, and we might do all sorts of other things. And so as we're going through the stack, the type is going to change. And we could probably, if we really wanted to, do some like really fancy work, kind of like we did in that session where we were doing the H set, where we like try to keep track of all that stuff. But we don't really need to or want to necessarily for performance reasons do that here. We just want to essentially say this is going to be an isolated part of the code where we're going to have less type safety internally. We're going to take on the responsibility for making sure that we do things in a way where we don't have a class cast exception. And we're just not going to expose that to our users. We're just all going to handle it ourselves. So this erase thing is just basically saying, it's just a helper for us to say, okay, within here, I'm going to work with a bunch of ZIO effects, and I'm going to know the way I construct things, that the way I'm putting them together is valid, but I'm not going to necessarily be able to express that at the type level. And then I'm going to create one more helper for myself that I'm going to call a continuation. And that's just going to be a function from anything to one of these erased values. And so if we go to the definition of flat map here and this continuation, this is basically exactly what one of these continuations is. So this is a continuation here. And then with those two, I'm going to actually create a stack. And again, I'm doing like bad things here. This is going to be a mutable stack. I'm going to be just pushing things and popping them off of the stack in a completely imperative, non-functional way. But I'm going to do this here in a way that it's not going to be exposed externally to our users. So now we're going to, instead of just matching on self, we're going to add one more concept here, which we'll call the current ZIO. And that'll be our self initially. And then instead of just matching on self, we're going to match on the current ZIO. And we're going to do this whole thing in a loop. Perfect. Okay. And so now we're going to match on the current ZIO. And so now our logic in some of these is also going to have to get a little bit more complicated, because now when we see a succeed case, we've got to ask ourselves what the state of the stack is. So one possibility is the stack is empty. And if the stack is empty, then that essentially means we're done with our work, right? There's no other continuation to do. And so if the stack's empty, we can stop looping and we can call the callback with this value. On the other hand, if the stack's not empty, then we need to pop a value off the stack. And then we can say current ZIO is equal to the continuation with the value here. And let's just, I think I probably created some compilation errors. I think we're missing a closing brace somewhere. Let's see. Here. Yep. All right. And now we've got a couple of other compilation issues. So I think maybe these need to be ZIO dot. Okay. And so now we're getting into a couple of these type safety issues here. And so basically, if you look at one of these, I'm getting a compilation down here because this is expecting, so when we defined the ZIO.fork thing, we extended ZIO fiber A. So this thing is supposed to be a subtype of fiber A, but this ZIO here is just a ZIO of A, right? That's kind of what self is. So I'm gonna give myself one more helper as part of this, like, just I'm taking on responsibility for type safety myself in here. And so this is just gonna take any ZIO, and it's just gonna forget that type. And because it's covariant, I actually don't need to do anything here other than just return that ZIO. And so then current ZIO can just be erase self. And so now if it's any, the fork can be a subtype of any, and we should be happy there, but now we're gonna have to do some more stuff. So now I'm getting an error here when I call the callback, because the callback is expecting an A, right? It's an A to unit, but now this value is an any. And so this is where, again, kind of saying we're going to do we're going to take responsibility for the types here. If the stack is empty, then that means we've gone through all the different steps in the computation. And even though the different steps may have different types, when I put all those together, I know that that's supposed to be an A. So if the stack is empty and I've implemented this right, then when I'm calling this callback, I know that this value actually is an A. It's not something else. And so it's safe for me to do this cast here. And I think I'm gonna have to do that a couple other places. Basically, whenever I do kind of the final callback here. And some of these I'm actually maybe gonna just like comment out for a sec, just so we kind of, because we're gonna have to come back to some of these. Let's see, even we'll come back to this in a sec. Okay, so now we've commented all those out. All these work. And nice, so Kit's gone ahead and he's created kind of a helper method here that's just gonna finish things off for us if we are done, and otherwise it's just going to pop another thing off the stack. So that's great. So with that, here then, we can just call complete with the thunk here. That's going to be happy. All right, so now we're ready to think about the flat map case. So the flat map case, we've got this continuation that, and so here, okay, so here I think we're going to have to do our own. So here we've got, we're going to want to add the continuation to the stack. So we're going to do stack.push continuation. And then we're just going to say current ZIO is this next one. So thinking about just the interpretation of what this means for a sec. So the ZIO.flatMap basically says, run this thing, and then when it's done, run this. And so what we're going to do is we're going to take, okay, this thing you asked me to do in the future, I'm just going to put this aside. I'm going to put it on the desk for now, come back to it later. I'm going to take this ZIO thing you said I'm supposed to run, and I'm going to just go ahead and I'm just going to loop through this. So I'm just going to run this thing next. And then when I get to something else and I'm kind of, I think I'm done, before I'm actually done, I'm going to go back to that stack. I'm going to say, hey, do I have anything else on my to-do list? And if I do, I'm going to take the next thing off and I'm going to run that thing. So just with what we have so far, we haven't yet implemented the async or the fork functionality in this new way. But just with this, if we've done this right, we should be able to now run our original program in a way that's stack safe. So let's see if we can do that. So this was one, oops, what are we doing here?
Well, I think we need to make it lazy, right? The constructor for zip, right?
Oh, do we?
We may not have made it call by name. And same with 84. And I guess, yeah, maybe same with zip width as well. Cool. So many howdies, yay.
So many howdies, 100,000 howdies, all the howdies you could possibly want. So that's kind of how you can solve stack safety. So one of the kind of easy wins when you move to this even more declarative encoding where you just have this one run loop here is that you get to put all that in one place. So we implement this one run method where we had our own stack that used the heap instead of the stack, which can just grow much larger. I mean, maybe if we had 10 million or something, we'd create a problem, but that would be a bad idea for independent reasons. But we basically have as much space as we have memory overall for our program here. And so now we can run these programs that just keep going and going and going.
Also, it's good to note, even though we did loop 1,000 times or 10,000 times, I don't believe our stack ever really had more than 1 or 2 values on it, depending, right?
Right. In this case, not. Yeah, we can do other more pathological cases where we can build up the stack, but in the ideal case, that's right. We just kind of keep popping one thing onto the stack and taking it off the stack. So let's now see how we implement these async and fork cases. So we kind of recover our original functionality, and then we can say, okay, we've really checked the box on implementing the stack safety feature.
Also, just as a tip, and maybe we could do this for next time as well, but if the stack concept is a little tricky, I think I kind of take it for granted now because I've done this enough times and explored it enough. But there are lots of good visualizations on the web because stack machines are very popular. This is just one particular implementation of one. But I definitely recommend sort of walking through it slowly. It's right, maybe on paper, just go sort of your own step-by-step evaluation of a very simple stack machine, perhaps like this one, and just get to the point by walking through it slowly where you can understand intuitively how it's sort of a direct translation of maybe the more immediately intuitive approach of, yeah, I'm going to call this and then I'm going to call that, right? It's this way of doing that in sort of an inverted manner. It's a little strange at first, but yeah, it can be.
Yeah, and maybe one thing to do after maybe we implement these is we could actually go back and maybe we could add some debug statements, and we could take like a simple statement, like example of like doing it like the 10 times or something, and see what that actually looks like through the interpreter.
Yeah, that could be helpful. But definitely, if you're confused and you want that, leave some comments, and maybe we can go into that more in depth. Prepare something.
Yeah. Okay, so let's think about this async case. So the async case, we've got this register function, which is actually expecting a callback itself. So just like some of these other cases, what we do here is going to depend a little bit on whether there's something left in the stack. So one case is that the stack's empty. And if the stack's empty, then we can stop looping and we can just call the register function with the callback. Thing we got to think about a little bit more is what we do in this case here. So this case means we've got this register function that wants some kind of callback, but we've still got more work to do before we actually have a value to give it. So what we can do here is we can call the register function and we can give it our own callback. And remember, the callback is just a function that takes an A and A to unit. So in this case, we could just say current ZIO is equal to stack.pop. Oh, excuse me, I think we got a, so I think this goes here, I believe. So we're going to just pop this off, and then we're going to say, oh no, sorry, we're just going to say, register AO, ZIO, succeed now.
You want it to be current ZIO instead of A?
Yes, yes, excuse me. Oops. And I actually think we need, let's see, no, that's right. Oh, no, sorry. Sorry, we're going to, excuse me. So here, once we have the A, we're going to say that const is equal to stack.pop. And then current ZIO is going to equal to, I believe that's going to do what we want. And so this is another area where just our lack of type safety is hitting us a little bit. So here we can give ourselves one more helper. So I'll call this erase callback. And this will take a callback data unit. Give us one more of these. Callback.
You had a capital B. Call back.
Oh, is it? Maybe I should not do that. Should not be relied on for typing here. Okay, so let's see how we're looking here. Okay, this is compiling. I guess we got some deprecation warning. So let's check ourselves and let's try. I think we've got an async example near the top. Let's try.
Yeah, there's a zip par one if you just run. It's one.
Yeah, I think we need fork for that one.
Oh yeah.
I think we've got an async one.
Oh, yes. Too.
There we go.
Nice.
So we got async working. And then our final one is fork.
Could you take a sec to sort of like walk through the logic there? Because it is a little trickier, right? I gotta.
Yeah. This one.
Where goes what? Like, what's the thought process?
Yeah, this one is a little bit trickier indeed. So basically, we're saying here, so this ZIO async case means we've got some asynchronous API that's gonna, when we call register, is eventually gonna call this callback that we have. So we say like, okay, start running this like third-party API. When you've got a result, then take the next thing off the stack and that next continuation, because we know we have a continuation because we said the stack wasn't empty, and give that and feed that value that you got back from the third-party API to the continuation.
I think we're actually missing something here. Don't we need to loop again at this point in some way? We need to sort of kick start our, because we've never stopped.
We never stop looping, right? We only, right, the loop is true and we only tell ourselves we're stopping here.
So what'll it do in this case? Because continuation is when it goes to loop, there won't be a current ZIO.
Oh, you know what? You're 100%. So I think
missing something.
Yes. So we need one more function here. Yep. So you're right. So we need to here, we say we want to stop looping. And then we can either set loop to true, or let's give ourselves a little helper. Let's call this resume. And here we're going to set loop to true. And I'm going to give this whole thing actually its own name. So maybe I'll just call this run. Yeah, that's 100% right. And so when I resume, I'm going to set loop back to true, and I'm going to call this whole run loop again. And so now, yeah, let's check our logic here. So if the stack's not empty, and in fact, now at this point, we can always set the loop to false if we want to. We're going to say, okay, we want to stop running right now ourselves. And we want to tell this third-party service, hey, as soon as you've got a result for us, and I think we actually don't even need to do this. We can simplify this. And we can say, set the current ZIO to ZIO.succeed now with the result you got, and then resume running the run loop. So let's try that. There we go.
And one extra thing that I did here was also add, because we have to call it at the end of this, well, other run method, sort of the outer run method. So I just called that at the end, because now that we've abstracted that into, now that we've turned run into its own internal helper method.
Yes, we need to actually call that at some point. Yep, 100%, 100%. Okay, perfect. Yep. Now we got that in good shape. All right, so then fork. This one is actually, yeah, I think the async one is probably the trickiest one here.
Yeah, and can we actually go back to that one?
Yeah, sure.
Sort of a recap. So I mean, everything is basically doing the same thing, which is we are, we might have some steps, these things called continuations, which are going to take the current result and well tell it how to continue, right? What's the next ZIO we need based on the A that we have? So we have that. So we may or may not have continuations. If we don't have continuations, then we stop. And then we are going to call this third party, this register thing that's going to get our results and give it the callback, which is, this callback is basically the continuation from the outside world. It's the continuation that the user has given us for how to actually escape this ZIO and do something real with the final result. So we're going to say, okay, third party API, you get to use the actual, you get the remote that the user gave us. So you get to continue with what the user wanted. However, if it's not over, then you don't get to continue with the callback that the user provided us. Instead, you have to continue with this run loop. And we do that by setting the current ZIO. That's kind of how we keep the current state of our stack, the value that the stack's going to use, and then we resume. And we know that we handle succeed by doing that method that we wrote up above, which is going to pop a continuation off the stack. So that's why Adam was able to remove that logic here, because it's already handled by the run loop, and this just simplifies that.
Exactly.
Kind of tricky. lot of steps, but definitely recommend when we post this, go through it if you want, if you're interested.
Yeah, and I think that analogy of like this being kind of some like third party like asynchronous API is like a really helpful one here. Because what we're saying here is like, okay, this is like, to do any more work, we need an A. We need a value to feed to this run loop to continue. But this async step says, hey, there's no value available right now. There's just this third party API you can call. So that's why we set the loop to false. There's no more work for us to do locally. And we just give this third party API an instruction of like, hey, when you've got a value available, put it here and then tell us to continue. And then once you tell us to continue, we'll go back to running the run loop and doing something with it.
It's all continuations all the way down. It's a complex idea, or a very simple idea, but which is very powerful. Continuations.
Yeah. So then the final case is this fork one, which I think will be easier. And so here, I think we are going to do something pretty similar to what we did in our original encoding. So we've got to actually create this fiber. And right now we're going to do that by doing this new fiber impl. And then if we go back to the definition of fork, fork extends fiber A. And we've got to remember this is the return value that this step is supposed to have. And other continuations might be expecting to do something with that step. You could imagine we did like fork the fiber and then we flat mapped and we did something else with the fiber. So we need to make sure that any step we're done with, we set the next value that the continuation is going to be using to take that fiber. So here we could just say current ZIO is equal to, I think we can even use our little complete thing, because I think we can just, oh, so good catch. Yeah, I didn't know if creating the new fiber started it or yeah. So exactly, we can get rid of that. And then we can complete ourselves with the fiber. And this way, if there are any continuations that are doing something with the fiber that are like going to join on the fiber or do anything else, that's going to work correctly. And we're going to maintain the integrity of our stack, because that's kind of the responsibility we take on when we have this encoding, is we've got to make sure that like when someone pulls something off the stack, they always get the type of value they're expecting. So now I think we should have all the components in place to implement our fancy example here. So I think we had this zip par one. So let's try that. I think that was 13. Okay, so I think we're missing something here because we began, but we didn't get the results here.
Mm-hmm.
So let's see. All right, so we started both of these. And then, oh, we call complete. The stack is empty. Let's pop the stack. Okay. That seems correct. Let's try it one more time.
Okay. Yeah.
Okay. So I think all right. So I think that this is going to be a good impetus for one of the other things we had was to take care of that concurrency issue. So I think we'll make that the next thing we do.
Nice.
But so I think at this point, if we go back to our little to-do list, I think we can put our little check marks next to stack safety. Maybe this will give us the tools to implement the execution context thing. But maybe since we just ran into it, handling the concurrency issue is a nice next step. How does that sound? Yeah,
that would be great. Yeah, and we have about a little more than half an hour left, so I think that would be a good thing to give us time to cover that.
Okay, so
if anyone has any questions also.
Yeah, please jump in here. And well, I'm screen sharing. I can't see as much, so yeah, please, we can stop at any time and do questions. Okay, so I think if we go to, yes, all right, so fiber impl here. So here's basically where we have the issue. Is right now this fiber impl has these two different vars as part of it. So one is this maybe result, which is supposed to contain the result of the fiber if it's done, so some A if it's done and none if it's still running. And then we've got this other var with callbacks that is supposed to have everyone who's waiting on the result of the fiber. And if no one's waiting, then it's empty. And right now, this is actually not concurrency safe, because we're going to have multiple other threads that are potentially interacting with this fiber. And right now, that's not safe at all for a couple of reasons. First, these aren't volatile or atomic variables. So we don't have any guarantee that if one fiber, if there's an update to that, someone else is going to see the update. Or that if you're updating, you're going to get consistent state. And there's also a risk of inconsistency between these two things, where you could, like, let's just say we complete this result, but then we haven't removed the callbacks yet. We could be in this kind of inconsistent state where we see like it's both completed with a result, but it's still got callbacks. So whenever we're dealing with these, a good approach is to think about the state we have, and at least the simplest thing is usually to encompass the state in a single atomic variable. If you have larger concurrent structures, like something like a concurrent queue or a hub, you can think about fancier ways to kind of break that state up into different pieces and ways to maintain consistency between them in a way that's more limited, but that's enough to guarantee the correctness you want. But as a starting point, thinking about having all of your state in one place is a really good starting point. And especially for something like this, it's probably also the right ending point, where if we really think about this, right now, these are really two sides of the same state. There are really only two possible states for this fiber. And it's either what we could call like a running fiber, in which case it doesn't have a result yet, and it has some people who are potentially waiting for its result, or it's a done fiber, and then it just has a value, and then there's no one waiting for its result because anyone who was previously waited got completed as soon as it got done, and anyone new who tries to wait on it just gets the value immediately and doesn't wait on it anymore.
What do we do in functional programming when we have like a piece of state that we want to like prevent some representations from being legal? What is that again?
Yeah, exactly. So what we could do here is we could create something like, let's call it fiber state. And this is, we're going to use it here, but you're going to see, like, if you look in like ZIO, if you look in some of the stream operators, you'll see a lot of stream operators, you'll see the same concept of us creating some concept of state that kind of tracks the relevant states that like this machine could have as we're going through, and we just kind of go between them. And so in this case, just because we're already in this class, I'm not going to bother with creating like a separate like object and things within the object, and just do it right here. So one possibility we'll say is we'll call this final case class running.
It already knew.
And let's call this like, we'll just call it callbacks, maybe. And so this is going to be this same list A to any here. And this will extend fiber state. And then the second possibility, we can call final case class done. So these are really the two possibilities for what the state of this fiber is. And we'll take that idea. For some reason, yeah, when you do final here, you can get an issue. So I'm just going to make it not final, which is, I think, yeah, kind of a weird thing, but fine. Okay, so now I'm going to want to have an atomic variable to encompass this state, because I'm going to want to make sure that everyone's always viewing a consistent view of this state. And like, maybe an easy way to think about it is, let's say we didn't have this. So let's say I just had var state, fiber state, and initially it's running with no callbacks. So if this is all I had, then let's say my fiber is running, it's running, and I have like 3 different people who are waiting for its results. So we end up having this result, this list that has 3 callbacks in it. If I don't have this be an atomic variable, then I could potentially have someone add another callback at the same time that I'm completing these, and I could have that other callback just kind of sitting there and hanging out there. So I want to avoid any issues like that. I always want to have people working with a consistent view of this state. So I'm going to import a atomic reference in here that's going to encompass these. And now I'm going to say val state, atomic reference, fiber state.
And for people who maybe haven't gotten to the nice low level Java concurrency operators, I'm certainly much less familiar with them than you are. What is an atomic reference? What is that? What behavior?
Yes. So what we're actually going to see in 1 second, we're almost going to be kind of implementing its core operation. But the idea of an atomic reference, maybe like a really simple example. I don't know if we actually have ZIO, the normal ZIO here to illustrate the problem. Actually, we could probably illustrate it ourselves. Sorry, I need to hide this again. Yeah, so let's actually, let's maybe comment this out. Well, maybe it may be hard to see since we have to fix this first. But basically, so let's say that I was doing something in normal ZIO code where I did like var I equals 0. And then I say for blank in ZIO.succeed, I plus equals 1, and then I try to fork this and repeat 10,000 times. And then I do value in succeed I value.
Mm-hmm.
So our normal expectation would be that, okay, I'm incrementing this thing 10,000 times. So at the end, it should be 10,000. But we can run into this issue of inconsistent state here, where anytime you do something with one of these values, like in this case, adding it, what you're really doing is you're saying basically, get the old value, do some operation on it, set it to the new value. So we have this like really natural intuition of like, we don't necessarily think about those as being different parts, right? We just think about like, oh, you're adding one to it. So you added 10,000 times to it, so it should be 10,000, and that should just work. But each of these is a different step. And if we have different fibers operating at the same time or different threads, these orders can get mixed up. So let's like just think about like maybe a really simple example. So let's say that these 2 processes are both trying to add 1 to this. So the way we would kind of expect things to work is this guy gets value of 0. This guy does some operation on it. So his operation is going to be 0 plus 1. And then he sets it to the new value of 1. And then we have the second guy, or I guess gal, if we want the fibers. The second fiber is going to get the old value, which in this case is going to be 1. And then they're going to do some operation on it, which will be 1 plus 1. And they're going to set the new value to 2. So this is kind of like our normal mental model of how the world works. And like this is great. But when we have, so this is all on thread number 1, and this is all on thread number 2. So when these are on different threads, there's no guarantee about the relation of these steps unless we do something specifically to create a relationship between these steps, which if we're just using a normal var, we haven't done.
So these could actually be in the real world interleaved, right? Where this,
right, exactly. So let's
like,
try, so let's see how we could create a kind of unexpected result. So this is kind of expectations in synchronous world. So now let's play with these and let's say one possible order of execution. And so let's say now, yeah, exactly. Yeah, that's a good, that'll make it a little bit easier for us to, and these will go away. Yeah, so now let's say I reorder some of these. Oh, there you go. So now thread 1 gets the old value of 0, and thread 1 is in the process of doing its updating. And then at the same time that's going on, thread 2 also gets the value of 0. So now thread 1 sets it to 1. Thread 2 is like, oh, the right number I should set it to is also 1. And now we get 1 instead of 2. So this is just like a simple example of how we can get thrown off because these guys are essentially kind of viewing inconsistent state or partially updated state, right? Of like, here thread 2 is basically observing the state of 0, even though thread 1 is like in the process of updating that state. So it's kind of observing a, you could think of it as a stale state. And this can lead to things, this can lead to all sorts of bugs that make things not work in higher levels of our code. So like even above when we like try to do that like zip par and like, oh, it didn't return, like, what's going wrong? Did we do something wrong with the implementation of zip par or the run loop? And I think the answer is no, I think it's actually this, but like, that's why like these concurrency issues can be super important, because if there's an issue like that in very low level code, it can make code like this much higher level not work. And like generally whenever you're working with like your own code and not working, like your expectation is like it's something you did at your level, and you know you can kind of spend a bunch of time like pulling your hair and being like, what did I do wrong? Even though like maybe it was actually 5 levels down, and then it's much harder for you to debug and you kind of need to probably go to other people. So when you're implementing lower level code, it's like really important to get this right.
Yeah, and
so,
it's super tricky because our intuitions about what is atomic, and just for silliness, I copied the dictionary etymology here because we think certain things are indivisible. We think, you know, I plus equals 1. It's 1 line of code, right? And it's so small. How could this be 3 different steps? We think this is indivisible, but instead, no, it's actually not atomic. It is not the base unit. Instead, this get, update, set are this sort of the atomic operations. So I think an atomic variable will allow us to regain our intuitive sense of what is truly atomic under certain circumstances, and once again create an atomicity there that works between threads, and yeah, therefore it doesn't create these really strange interleavings of substeps which seem invisible at the syntactic level to us. But you know, when you go to bytecode and you go to the actual computer doing stuff, it works on a very small scale. So also I came up with a new nickname for Adam. We call him Adam Fraser because he's so good at this low level stuff. There we go.
So when we say something is atomic, we're generally getting it from this Java util concurrent atomic package. And what it effectively means is that when you observe your program, you'll never be able to observe an interleaving like this. There are essentially only 2 possible orders of execution you can observe. You can observe this one, or you could observe the opposite. You could observe thread 2 getting the value of 0 and setting it to 1, and thread 1 getting the value of 1 and setting it to 2. It's not legal to interleave these steps. Now that's the experience you're going to have as a user. What we're going to see in a second is it'll depend a little bit on exactly which atomic one you're working with. And as a user, you won't have to worry about this, but that's actually often not the way that it's actually implemented by the machine. So if you have something very simple like an atomic integer and you're using just like get an increment, depending on the architecture, it may have a specific instruction that like literally does that as one machine instruction. And so you don't need to do anything else for that. But when we have something like this atomic reference here, this atomic reference definitely doesn't fit in one piece of memory on the machine. So it's not possible to just like literally do this as kind of one machine level operation. And so what these atomic variables end up being implemented in terms of is something that you'll see is called CAS, or compare and swap. And what compare and swap means is that we're actually not going to prevent any of these arbitrary interleavings from occurring, but we're just going to do one more check. So basically, instead of our logic being this, we're going to make this step a little more complicated, and we're going to say, set it to new value only if equal to old value. And we'll say otherwise, go back to first step. And this thing is going to need machine level support basically, because this step of the setting and the checking whether it's equal to, these need to occur atomically. But that can be supported at kind of a lower level than just this like updating a reference. So actually we'll kind of use that tool ourselves in implementing that. But what that means is that if you go down to an interleaving like this, this actually could potentially occur, and maybe could occur multiple times, but each time it does, at least one of these threads is going to retry. So like if we look at this example here, okay, thread 1 gets the old value of 0. Okay, that's okay. Thread 1's doing its operations. That's great. Thread 2 gets the old value. Okay. Thread 1 sets it to the new value. And so in this new world, it's going to set it to the new value and check at the same time if the old value is equal to what it expected. So it's going to say, is the value equal to 0? If it is, set it equal to 1. And it can say, yep, the value is equal to 0, so I'm going to set it to 1. Now thread 2 does its operation. And then when thread 2 goes to set it, it says, hey, I want to set the value to 1 if the value is currently 0. But now the value is not 0 because this other guy set it to 1. So now thread 2 says, uh-oh, I got in this inconsistency here. I need to retry. I need to go back and do all my logic again. And so thread 2 here is then going to go back. It's going to get the value, which is now 1. It's going to do the operation again. So now it'll do 1 plus 1 equals 2. Then it'll do the same check. And now, assuming nothing else has happened, it's going to say, okay, the starting value is 1. That's the value that it currently is. I'm going to set it to the new value of 2. And so what we're going to observe is an ordering like this, but that's not necessarily everything that happened. Depending on how many threads are hitting this thing at the same time, there could be a bunch of retries going on. And that's why, like, if we think about these low-level concurrency operations, one of the things we think about is how many of these threads are interacting with one of these atomic variables at the same time. Because the more that are interacting with at the same time, the more they potentially have to retry and the slower we're going to be. So that's where sometimes we like try to split that state up into different parts of the state so that different threads hopefully interact with those different parts and force each other to retry less frequently.
And this is also probably why it's not always, parallelizing doesn't always immediately mean things are going to go faster, right? If it's, yeah, because there's clearly more work being done here, and given the right circumstances, you can actually create more trouble for yourself.
Yeah, not to mention submitting all these things to an execution context and that potentially spinning up new threads, or at least allocating things to new work queues and getting them from work queues. So that, yeah, that's 100% right. There's a trade-off in parallelism here. Okay.
That was great. That was a super great introduction, because I know, like, you just see in the literature, you just see CAS all the time in all caps, CAS. Like, what the heck is CAS? And you can't really Google it very easily. So yeah, CAS, compare and exchange. This machine code, this machine level operation that you can express at a high level in Java and Scala. Yeah, awesome. That was very valuable to me as well.
So let's get some experience with that, with this thing here. So we've got this state thing, which is one of those atomic things that's going to give us that compare and set operation. And so
is it compare and set or compare and swap? I guess compare and set in this case.
In this case, we're going to do compare and set. You can do compare and swap, and they're kind of two slightly different operations, and sometimes one supported versus the other on different architectures or Java versions. Yeah, I think you can kind of use either term.
Yeah. Do you happen to know, just for fancy purposes, whether the acronym stands for one or the other, or just kind of it's ambiguous?
I think compare and swap is like probably the one you'll most see in the literature, but I think both of them.
Okay.
Okay. So now that we've got all of this, let's find where we're doing our operations that are involving this. So I think we've basically, our key one is the join operation here, and then the actual completion of the result. So maybe let's see, where are we doing maybe result? Oh, here. Okay. So here before we were setting this variable, we're basically going to want to get rid of these two variables. And so this is not going to make sense anymore. And so let's think now about what we want to do when we get this value. So this fiber is running, it's doing its thing. It's finally got its result. So what we can do, and maybe actually maybe I'll actually do this logic up here. Let's put a question mark here right now.
Oh, and could we close the terminal just for that extra?
Oh, yeah, definitely.
A little bit of screen real estate. Thank you.
Yep. Okay. So the first thing we're going to want to be able to do is we're going to want to be able to complete this with some result. And so we do that when we're working with these low-level atomic ones. We're going to need to do some kind of loop. So I'm going to create a loop for myself. And then while we're looping, so the first thing I'm going to do is I'm going to get this state. And maybe I'll call this old state for myself. So old state is going to be state.get. And so this you can think of as like a snapshot of the state as of a point in time. So I'm going to grab the snapshot of the state as of when I start this. And so this is going to be one of these two things. It's either going to be running or done. So let me just pattern match against this to say which one it's going to be. So one situation is it's running and it's got a set of callbacks. So what I really want to do here is I want to complete each of the callbacks with the result. So I want to do something like callbacks each result. That's what I intuitively want to do. That's not actually what I want to do, because one of the things that we want to remember whenever we're working with these atomic variables is that we want to do as little as possible between getting and setting. So if we go back to here, we've got to remember that if I get and then something else happens to change the value of the variable, when I set, I'm going to have to retry. And so I definitely don't want to do things that are potentially long-lived, like calling all these callbacks within this loop, because that's going to increase the risk I have to retry. And actually, in this case, there's an even bigger reason that I don't want to do this, which is anything in this loop could happen multiple times because I have to retry. So I don't want to do anything that's observable to the outside world that's going to potentially, like, I mean, let's say this callback is going to like print howdy. So then I could be trying to print howdy once, and I could see howdy getting printed like 3 times and be
What's wrong
like,
with that? That's a great. That's more howdies the better.
not when they're unexpected howdies. If you only want one howdy, you know, you gotta respect
Rude.
that.
Still rude. Yeah.
So what I'm going to do here is all I want to do here basically is just return the callbacks. So I'm going to create some I'll call this toComplete, and this is going to be a list any, and maybe I could set that to null initially or set that to list.empty. Again, we're doing kind of low level stuff here, but right now, fine. Let's set that to list.empty. So if we're running, then I want to set toComplete equal to the callbacks. And then I want to do this compare and set thing. So the way I can do that is I can do state dot. Yeah, and so this gets to this like compare and exchange and compare and swap thing. The compare and swap is like what you see more in the literature, but it's actually interesting. I think we ran into this once with the hub actually, where compare and exchange is not supported on older Java versions, which is kind of the most direct equivalent of the compare and swap. It's the kind of the compare and set. But anyway, we're going to do compare and set here. And so this compare and set takes these 2 parameters of this expected value, which is basically the old value. This is the value that you want to make sure it's equal to. And then the new value, this is the value you want to set it to. So I'm going to say if the state's still equal to the old state, then I'm going to set it to done with that result. And this is going to return a Boolean. So this Boolean is true if I successfully compare and set this, if the state really was the old state, and it's going to return false otherwise. And so if it's true, then I'm done. I don't need to continue. So I can actually just say loop is equal to, it's not the case that I compare and set, right? So I'm going to try to compare and set. And if I fail, then I'm just going to do this whole thing again.
Mm-hmm.
And that way I'm just going to keep redoing this until I get a consistent state. And then the guarantee I'm going to have from this is that this toComplete value, by the time I break out of this loop, I will have set toComplete based on a consistent state. So I've handled the running state. I have one other state here. So this state should basically never happen.
Yeah.
Because this means that a fiber has been completed twice. So here, I think the only
throw an exception, blow up, yeah.
Yeah, basically there's, so here we could say something like
inconceivable.
A new exception. Defect. Fiber being completed times. Okay, so now I'm done with this whole loop. And I've gotten this list of 5. So what I've done so far is I've set the state to being done, which I want to do. And now I've got all these callbacks. And now I can say toComplete for each callback, call the callback with the result.
Would it also be possible to do something like just checking to see if this, and then if that is the case, then do the callbacks dot for each with the result? Would that also kind of be identical? And then removing the to complete stuff? Or is there a reason? I'm just curious. Would there be a reason not to do that? And then also adding loop to false in here? Because this would only get triggered if you were done. So if
Yeah, that's totally fine. I mean, those are kind of semantically equivalent. I think sometimes for style, I kind of like to do like in terms of logic flow, that's the same. I think sometimes I like to just like have the entire atomic block kind of as one thing. And so I kind of know like, okay, I'm doing like that part of the world here. And then I'm doing other things, but logically those are equivalent, because once essentially you've done the compare and set, you're done with the atomic block. So anything you do after that, it doesn't matter whether it's here or here. And I mean, maybe that's nice because it lets you not define this additional bar. So that's totally fine.
Yeah, and I wasn't sure. I mean, because I like that principle a lot of doing as little as you needed to between steps. And I guess in that way, there's one less assignment, right, to an intermediate var. I'm not sure if that's going to matter really, if the performance is going to matter at all there. But that does save one little tiny operation. And then we have to set loop to false. And then just, if it's done, we set it. Okay.
Yep.
Cool.
Okay. So now we've got completing it. And so the other operation we've got to have is we've got to have a wait. And so a wait is going to take a callback. And it's going to add the callback to this thing. And so do a pretty similar thing here.
Who could I try with my my new knowledge?
Yeah, go for it.
Sorts of things.
Yeah.
Okay. We'll see if this makes sense at all. Okay. So looks like we definitely want the old state, right?
Yeah.
Kind of the first thing to do, and then we want to match on it. That's pretty easy. So old state match. Okay, and I'm just going to copy. Okay, we have running. And we have done, and I think both of these cases make sense in this case, right? Because they've already been running, and we need to add our callback to that. Otherwise, not. So let's focus on that case first. So actually, maybe the done case is even easier potentially, because we don't need to then modify anything, right? If it's done, we can actually just stop looping because we're not going to modify anything. We don't care. We can keep it done with the result. That's sort of locked in. And we're also going to, I guess doesn't matter what order, I'll call the, our callback with the results. So I think is that fine for done? Okay, the running case is the more difficult case. So we're probably gonna maybe do this sort of thing again, where I wanna compare and set, and I wanna all see as the old states. But I want to update it. So I kind of do need the new state. Maybe I'll break this out here just for clarity, which will be the running with our current callback, I guess prepended or whatever, appended, I'll prepend it.
Yeah, I think right now we don't have really clear semantics about the ordering of the callbacks. Yep.
Yeah, and then, I mean, in this case, maybe now it would be nicer to do loop equals not that. So we just want to update it really. I mean, that's kind of the only thing to do.
Right, right. If it's still running, then all we can do is add ourselves and then we're done.
Yep, and then it'll be updated for the next time. Okay, cool, and that'll stop it if it succeeds. Otherwise, it'll keep trying, during which it might still be running, and then we'll add it to whatever the new list of callbacks. So someone else added a callback, or it was completed.
Or it'll be completed, and then we'll be done.
And then we'll just call ourselves, and we don't need to worry about anything. Cool.
All right. So now I think we've got the right tools there. So now we should be able to plug this in here. And now this can really get a lot simpler. So now we're just going to run this. And when we've got an A, let's see, what scope do we have this in?
I think it's just complete, right? And then a wait.
Yeah, I just want to make sure we've got, oh yeah, we're in the same scope. Okay, perfect. So yeah, so here we can just do, yeah, I think we can even just do run complete. And so this is also like, you can kind of encompass that like tricky low level logic in a single place, which also makes it easier if you do have any issues there, you kind of just have to do it in that one place.
And then I think await is going to, oh, I think so. Await is gonna, we do need to return a ZIO, but I guess in
So
this
you
case,
just want to do ZIO.async.
yeah, I think in that case, we just have this case to simplify things.
Yeah, and then I
And-
think it's
and then
just call await with the callback.
Yep, which is, yeah, that little callback here. Callback. Nice.
Okay, so that was us doing a lot of coding. So let's.
Oh, required units. Oh, because it's an NE. I guess that's fine. It's whatever. It's the NA. I'm just going to
Okay.
change it to the NE up here.
Yeah, perfect.
Okay.
Okay.
Nice.
All right, so let's see if that works better. So I think we were doing our zip par example. Oops, no.
Woo! Nice. And I think one way that one thing I needed to do in order to make it not break was if you go to the zip par implementation, last time I needed to do this just because of that race condition.
Right.
I wasn't able to do the slightly simpler version, which would have been not to fork both, but just to fork one.
Yep.
But now we should be able to just do that, and that should work too, because that was caused by sensitivities to it not being very safe. And there we go. We could probably run that a bunch of times. I believe you that it will work.
Yeah, and I think the other thing we can do is I think another thing we've done is we've added this thread.sleep here, right? Because we're worried things were incomplete too early. So I think we can get rid of that now, which will just make things, I think, a little snappier. There we go.
Oh, okay. All right.
So
I thought that was running off in the background, but I guess, yeah, that makes sense. Awesome.
yeah. So yeah, I mean, we're basically at an hour and a half here. So I think that was, I mean, we covered both kind of moving to a more declarative encoding as well as low-level concurrency stuff. So yeah, so I think we can now put a, I haven't done that, but we can put a check on this. And we've definitely got some more work for continuing our series, but I think good progress for the session.
Yeah, that was, oh, I'm happy with it. That was awesome. Yeah, we saved the good low-level concurrency stuff to the end. Maybe we should also do another full session just on even more juicy compare and swap, whatever, all these other operations and different sorts of atomic tools. Because yeah, you're good at that, and it requires a slightly different way of thinking. That you know, doing the nice. You can live in the high-level world where everything is beautiful. You don't worry about performance or memory or concurrency, and this sort of, you have to flip everything. But it can be equally satisfying and equally challenging. So yeah, that was fun. I don't know.
That was
If there are
awesome.
any, yeah, thanks, Adam. And if there are any questions, you know, throw them in the Discord and leave comments anywhere, and we'll get these videos up hopefully in time for next Friday, so people can catch up with everything and rewatch if you need to, if you're interested. But yeah,
Perfect. And we'll push this up.
Yep.
All right. Thanks, everyone.
Till next Friday. Good day. Howdy. Howdy. Inverse howdy.
Bye.